Hello, everyone. Can you hear me okay? Yeah, good. Good morning, and thank you, Benjamin, for the very nice introduction of stellar activity, so I don't have to repeat too much about that. So today I'm going to talk about a study that I performed during my PhD at UCL. So during this project, I looked at a population of 20 different exoplanet atmospheres observed with the Hubble Space Telescope, covering from the optical to the near-infrared wavelengths, and finding widespread evidence for stellar activity. So to perform comparative exoplanetology, there are a few conditions that should ideally be met. The first one is that exoplanet spectra should be simultaneously observed across the broadest possible wavelength range in order to mitigate the effects and the difficulties of observations taken at different epochs. These are, for example, coming from an active stellar host or the variability from the atmosphere of the planet itself. A second condition for large-scale population studies should be that planetary atmospheres be observed by a single instrument or by combining multiple calibrated instruments on the same telescope. And this is to mitigate potential instrumental offsets. So to address these first two conditions, one of the possible choices of telescope could be the JWST. However, there are some limitations with this mission. The first one is that JWST covers the wavelengths longer than 0.6 microns, so it completely misses the optical where, for example, stellar activity or ASIS affect the exoplanetary spectra the most. Secondly, most of the data acquired by JWST is still private, so it is hard to perform large-scale studies with the publicly available data. Fortunately, in the near future, exoplanet-dedicated missions like Ariel and Twinkle will obtain hundreds of observations for a variety of exoplanets, covering simultaneously from the optical again to the near-infrared. So we will get a much larger and better picture at the sample of exoplanet atmospheres in our galaxy. So what we can do in the meantime is to leverage more than 20 years of observations taken with the HST, and in particular using the STIS and WFC3 instruments. The third condition for a large-scale population study should be to use a single data analysis pipeline to reduce homogeneously all data sets in the effort to mitigate reduction biases. So for this study, we use the Heracles pipeline, which has been developed specifically for HST data, but that has also been used to reduce JWST data. Finally, robust statistical tools should be used in order to perform quantitative comparisons and allow data interpretation. So in this work, we utilize TowerX3, a fully Bayesian retrieval framework, together with the Astera plugin developed by Alexandra Thompson, also a PhD student at UCL, that specifically focuses on correcting for stellar activity during retrievals. So here I'm showing the sample of exoplanets that we include in our study. We mostly focus on gas giants, but we have a very heterogeneous picture. So we go from sub-Neptunes all the way to inflated Jovians with a variety of planetary radii and equilibrium temperatures. Also, the exoplanet stellar hosts that we probe are quite varied. We mostly look at F and K stars, but we also have a couple of G and M stars. So the goal for this study was to determine the origin of the different spectral features that we see in these exoplanetary spectra. So using Heracles, we reanalyzed more than 50 STIS observations and 40 WFC3 data sets. And here on the right-hand side, you can see the results of our data analysis. But one of the things that might actually strike you the most was that when we have multiple observations obtained with the same STIS grating, we actually see differing features for the same planet when these observations were taken at different epochs. So to handle these divergent STIS spectra, what we do is to model different combinations of data sets as separate spectral scenarios for each planet. And to perform the atmospheric retrievals, we actually start off with a very simple model that contains a primary atmosphere with water as the only absorber. And then we progressively add more complex features, for example, gray clouds, alkali metals, and finally stellar activity. So to understand the impact that stellar contamination has on this sample of exoplanets, what we do is to use a variety of metrics, some that have been extensively used in the literature and some others that we developed specifically for this study. So the first one that we utilized is the base factor, which is defined as the ratio of two model evidences. In this case, we compared the evidence coming from the application of a stellar activity contamination model versus the evidence of a quiet star model. So by putting together all these results for the different planets, we see that nearly half of the targets exhibit a strong preference for the active star model. Even though this is statistically penalized because it has 4 more parameters in the model compared to the quiet star model. The second metric that we developed and we used in this study is called the stellar activity distance metric, which we use to quantify if an active star model fits the observational data better than a quiet star model. For this metric, we only considered the data points shorter than 1 micron, and this is because, again, the stellar activity imprints most of its signatures in the optical regime. The way the stellar activity distance metric is defined is such that if we get a value higher than 1, this means that the stellar activity contamination model fits the data better, so it prefers the data prefers this model. Conversely, if it is smaller than 1, it means that the quiet star model fits the data better, and if it is around 1, either model adequately explains the data. So as you can see here, we really get a mixed bag of results. For some planets, we get an ACD even close to 3. For some others, around 1 and even below 1. Finally, the third metric we employ is the stellar activity temporal metric, which assesses the repeatability and consistency of observations. So with this metric, we forget about the retrieval models and we focused solely on the data. So we compare basically different data sets acquired with the same STIS grating for each individual planet. And what we find from the overall results is a bimodal distribution in the SAT values, meaning that the variations that we see in the visible regime are either minimal, so we're talking about variations in the 1 or 2%, or moderately significant, so higher than 5, roughly between 7 and 10%. So putting all these results together, we concluded that stellar activity has a predominant influence on exoplanet spectra at a population level. And here what I'm showing is the results that come from this analysis. So using standard competition style ranking, we ordered the planet in our sample in order of most likely to be contaminated by stellar activity, which is WASP 6b, to the least likely, which is WASP 39b. Also, the color coding that we use is indicative of stellar activity. So green means unanimous or nearly unanimous indications for stellar activity. Yellow, it's a mixed bag, so we get uncertain indications. And when I use the red, we mean that we find a predominant preference for an inactive star. So I'm going to leave my summary slide here, but I would like to conclude with a message for the community, which is to please consider stellar contamination in your transit studies, because we see there is a widespread effect and needs to be taken into account, even though it might not be there, but it's still important to take into account. And also, as a community, I think we should strive to perform long-term stellar monitoring for these stars, not only the ones that I presented in this sample, but in general for all stellar hosts. So yeah, if you're interested in knowing more about the study, I leave here the link to the paper. This is going to refer you to the archive paper, because it actually has been published just today on APJS. But yeah, I still have 1 minute, so I will quickly jump over this mission. So just a quick advertisement here. If you are interested in monitoring stars, especially bright stars, for long periods of time, looking for stellar variability, stellar activity, even considering flares, then maybe the MOVE mission might be for you. So yeah, if you're curious to know more, please come talk to me, and I will be very happy to give you an overview. Thank you.
Elizabeth Newton, Dartmouth College. I was wondering whether you had compared the results from the transmission spectroscopy about which stars were active to other more standard like stellar astrophysics indicators, so like rotational variability or high energy emission.
Yeah, so we did an extensive study and research on the literature. So we really looked at previous exoplanet transit studies, also at the stellar literature, and so in the paper you will see a whole appendix where we report previous studies and also stellar activity indicators such as the S-index. So yeah, everything is reported in the paper, but in general, yeah, we find that our results are mostly in agreement with previous literature.
Natalie first, and then you'll get a sticker.
Hi, great talk. Natalie Allen, Johns Hopkins University. I was really interested in the table that you showed of targets, because just going through them a little bit, there are some targets in there that we know are active because they have spot crossing events like WASP-52 and HAPP-11 that are either in or WASP-80. There's kind of like one in each category that are known at activity from things like spot crossings. Do you think that there's a reason that specifically stars that have a lot of spot crossing events wouldn't be caught by this method that you guys are using?
The thing is that, for example, for HAPP-11b, we do know from previous studies that it is a very active star. Although what we find here is that, we're not really certain that for these observations actually the star activity was caught. But again, these are not like final results. So we don't want to say just take this as the ground truth, but it's more like to show that actually stellar activity is important. And also it can happen that during the time of the observation, maybe the star wasn't particularly active. So we might have missed that because again, these results are just coming from like maybe 1 or 2 observations of the star. So it's really hard to tell, if the star is not active at all or just wasn't very active at the time of the observation.
Is that a quick question? No. Well, yes or no answer. Okay, yeah, go for it.
Yeah, so Michael Radica, Chicago. I'm curious whether you use any different data cuts. So for example, you said you just kind of looked at blue words of 1 micron. I'm wondering whether you also consider like a cut, for example, red words of 0.6. The reason I ask is that, like you said, JWC kind of cuts off there. And so whether we might be missing or misidentifying some stellar contamination because we're lacking that like blue words of 0.6.
Yeah, I think it's really important to have optical data. Ideally, as I said, like you should have like optical data taken at the same time as your transit observation. But if not, then yeah, any optical data will be very useful, just to give you an idea of the activity of the star.
All right, let's thank Ariana again.